Electricity. The key areas covered today will be balanced Wheatstone bridge circuits, unbalanced Wheatstone bridge circuits, and resistor relationships. What we will do today is calculate the value of unknown resistors in a Wheatstone bridge circuit, look at the relationship between potential differences and resistance in a Wheatstone bridge circuit. Wheatstone bridge circuits. A Wheatstone bridge has 4 resistors arranged in 2 parallel branches, each of 2 resistors. The Wheatstone bridge is used to find the values of unknown resistors. A voltmeter is connected between the midpoints of the pairs of resistors in each branch. We can see a diagram of this here. When the reading on the voltmeter is 0 volts, there is no potential difference between X and Y, and the bridge is said to be balanced. A Wheatstone bridge can also be used as an input circuit in electronics. We can see an example of this just here. A. The balanced Wheatstone bridge. Consider the following circuit with 4 resistors R1, R2, R3, and R4. Current from the battery will flow through the 2 branches of the circuit. The resistance of the current path AXB is 12 ohms, therefore the current in this path is 1 amp. This is calculated using V equals IR, where V equals 12 volts. The potential difference across the 8 ohm resistor is 8 volts, again using V equals IR, where I equals 1 amp, which has just been calculated. Therefore, the potential of point X is plus 8 volts. The resistance of the current path CYD is 6 ohms, therefore the current in this path is 2 amps, again using V equals IR, where V equals 12 volts. The potential difference across the 4 ohm resistor is 8 volts, V equals IR, where I equals 2 amps this time. Therefore, the potential at point Y is 8 volts. There is no potential difference between points X and Y, and the voltmeter reading is 0. The bridge is then said to be balanced. When the circuit is balanced, the voltmeter reading reads 0, i.e. the potential difference between X and Y is 0. Resistor relationships. Relationship among the resistors in a balanced Wheatstone bridge. When the bridge is balanced, VAX equals VCY and VXB equals VYD. So, replacing this with our Ohm's law, VAX becomes I1R1, and that's equal to I2R2, and I1R3 equals I2R4. Dividing these equations, we get I1R1 over I1R3 equals I2R2 over I2R4. We can eliminate the currents in this and get R1 over R3 equals R2 over R4, or rearranging this, we get R1 over R2 equals R3 over R4. Note, the labels for the resistors, i.e. 1, 2, 3, 4, only apply to this setup. In general, it's the position in the circuit which is important, not the numbers themselves. To calculate the value of an unknown resistor, 2 of the resistors, for example R3 and R4, are known. R2 is a calibrated variable resistor, which can be changed until the circuit is balanced. The value of R1 may then be calculated. A galvanometer is a sensitive meter that can be used in place of a voltmeter. A galvanometer can only handle very low potential differences. A resistor is connected in series to the galvanometer to prevent damage to the meter when the bridge is far out of balance. Switch S is used to short circuit R when near balance to give greater sensitivity. Example 1. A. If the bridge is balanced, calculate the value of resistor S. We want to use our equation to do this. R1 over R2 equals R3 over R4. We have been given 3 values up here, 1 kiloohm, 2 kiloohms, and 3 kiloohms. So substituting those into our equation, we get 1 kiloohm over 2 kiloohms equals 3 kiloohms over RS. Rearranging this, we get RS, that's 2, RS equals 2 kiloohms times 3 kiloohms over 1 kiloohm. In total, this is 6 kiloohms, and that's what our RS is equal to. Part B. After a period of use, the potential difference across the battery and the circuit decreases to half its original value. What effect does this have on the voltmeter reading? This will actually have no effect on the voltmeter reading at all, as our bridge is still balanced in respect to the resistors. So part B, no effect. B. The out of balance Wheatstone bridge. The graph below shows the variation of potential difference between X and Y as one of the resistors is changed by small amounts from its value when the bridge is balanced. What we can draw from this is the out of balance potential difference is directly proportional to the change in resistance, i.e. the change in V is proportional to the change in R if the change in R is small. This linear variation of potential difference with change in resistance is used in electronics. For example, if one of the resistors is replaced by a heat-sensitive resistor, i.e. thermistor, then the out-of-balance voltmeter reading indicates temperature change. Example 2. Describe how the out-of-balance voltage in a Wheatstone bridge circuit can be used to measure temperature. R4 is a thermistor which is placed in melting ice. R1, R2, and R3 are adjusted until the bridge is balanced, i.e. until V equals 0. R4 is now placed in boiling water and the reading on the voltmeter is noted. A calibration graph can now be drawn. Any temperature can now be estimated from this graph that we've drawn. In drawing the graph, we have assumed that the relationship between the out-of-balance voltage and temperature are linear, so forming a straight line. Example 3. A Wheatstone bridge circuit is shown. A. Show that the bridge is balanced when the variable resistor R4 is set to 37.5 kiloohms. B. The variable resistor R4 is now set to 37.2 kiloohms and the potential difference between the points X and Y is measured. The resistance of R4 is then altered to the value shown in the table. Complete the table to show the voltmeter readings, including sign, that would be obtained for each of the remaining resistance values. First, let's have a go at part A. Show that the bridge is balanced when the variable resistor R4 is set to 37.5 kiloohms. We can show that this bridge is balanced by using our equation. R1 over R2 equals R3 over R4. R4 should end up at 37.5 kiloohms, but we won't put this into the equation straight away. Let's use our other numbers and see if R4 turns out to this number. So we have 3 kiloohms over 5 kiloohms equals 22.5 kiloohms over this R4. Rearranging this, R4 equals 5 kiloohms times 22.5 kiloohms over 3 kiloohms. Putting this into our calculator, we get 37.5 kiloohms. Let's try part B now. Our variable resistor R4 is now set to 37.2 kiloohms and the potential difference between the points X and Y is measured. We've got a table of values just here showing the small changes in resistance and we've got 1 voltmeter reading. We know that the change in voltage is directly proportional to our change in resistance if our change in resistance is small, which it is in this case. So we can see from the last part of the question that 37.5 kiloohms is when our Wheatstone bridge is balanced. And just here we can see that from 37.5, 1, 2, 3 divisions, so 3 of 0.1 kiloohms, is showing a reading of minus 22.5 millivolts. So if we divide minus 22.5 by 3, we get minus 7.5, and that's per 0.1 kiloohm. So all we need to do is take minus 22.5 and take away negative 7.5. We get to minus 15 for this one just here. We can take away negative 7.5 again, and we get to negative 7.5. And do the same again, we get to 0, which is where we should do because our bridge is balanced here. And then again, we get up to 7.5, and that's positive this time. So we've just completed the table to show our voltmeter readings, including our signs. Let's try some past paper questions. A Wheatstone bridge circuit is set up as shown. The bridge is balanced. A student suggests 3 different changes to make the bridge unbalanced. Let's take these statements one by one and figure out if they are correct or incorrect, as our question is wanting to know which of these changes would make the bridge unbalanced. So for number 1, let's look at our equation. R1 over R2 equals R3 over R4. The statement is saying double the value of R1 and double the value of R2. So let's put 2 in front of R1 and 2 in front of R2. Is this still equal? Well, we can actually cancel those values just here. So R1 over R2 is still equal to R3 over R4, so this bridge is balanced. Let's look at statement 2. Again, taking R1 over R2 equals R3 over R4. The second statement saying double the value of R1 and double the value of R4. So a 2 in front of R1 and a 2 in front of R4. Unfortunately, we cannot cancel these out. They're on opposite sides. If we wanted to get rid of either of the 2's, we'd have to take them across the other side, but then they would multiply. So in fact, this is not correct. This would be unbalanced. Let's look at statement 3. Double the voltage of the supply. We know that changing the voltage does not affect this resistor relationship, so we don't need to change any of our values just there, so our bridge is still balanced. So overall, it's just statement 2 that makes the bridge unbalanced, so our answer is B. 5 resistors are connected as shown. What is the resistance between X and Y? If we're a little bit confused by the way this circuit looks, you can actually draw it out slightly differently, putting in some straight lines. So we're starting at point X. We can turn this section into a straight line with 3 points coming off of it. On the top row, we have one resistor. We can ignore this corner just here because it's still just one wire going across, and put in our next resistor. In the middle, we've just got one resistor, and on the bottom, similar to the top, we've got 2 resistors. We can then connect these back up again and go to Y. Now this is much easier to look at as we're used to combining resistors in parallel when they look like this. So we have 30, 30, 60 in the middle, and 30 and 30 on the bottom. If we look at the top row, we have 30 and 30 ohms. We can just combine these as in adding them because it's in series in the top row. So top branch, R1 equals 30 plus 30, which is 60. Our middle branch, R2, is just 60, we don't need to do anything to that, and our bottom branch, R3, again is 30 plus 30, which equals 60 ohms. Now we can use our relationship for resistors in parallel. 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3. Oops. Therefore, 1 over 60 plus 1 over 60 plus 1 over 60 equals 3 over 60. And so RT by itself, if we flip our fraction, we get 60 over 3, which is 20 ohms. This is answer B. The diagram shows a Wheatstone bridge. The reading on the voltmeter is 0. The variable resistor, RV, is now altered in steps of 1 ohm, and each corresponding reading on the voltmeter is noted. Which of the following graphs shows how the reading on the voltmeter, V, varies with the change in resistance, delta R? We know that our change in voltage is directly proportional to our change in resistance when our change in resistance is small. Our change in resistance is 1 ohm compared to resistors of value 10 kilo ohms, so we've definitely got a small change in resistance, so the statement holds. Out of all the graphs, the one showing a directly proportional relationship is graph D. You should also be recognizing graph D from earlier in this PowerPoint. A Wheatstone bridge circuit is set up as shown. When the variable resistor R is set at 600 ohms, the bridge is balanced. When R is set at 601 ohms, the reading on the voltmeter is plus 2.5 millivolts. R is now set at 598 ohms. What is the reading on the voltmeter? Again, we know that the change in voltage is directly proportional to our change in resistance when our change in resistance is small. In this case, the resistance is changed by 1 ohm with respect to hundreds of ohms, so our change in resistance is small, so the statement holds. So if adding on 1 ohm, so going from 600 to 601, is equal to a change of plus 2.5 millivolts, Then going from 600 to 598 ohms, i.e. taking away 2 ohms, that is equal to negative 5 millivolts. So one step is 2.5, negative 2 steps is minus 5. That is an answer of B.